Georges Comte from Université Savoie, Mont, who will talk about Fourier transform of subanalytic functions. So please.
Okay, I hope that everyone can hear me. I first would like to thank the organizer for giving me this opportunity for this talk, which is a joint work with Ralph Kers, Dan Miller, Jean-Philippe Rollin, and Tamara Servi. The general problem we would like to address in the talk is the following. We take a function g with two tuples of variables x and y, and we try to understand or study the interplay between the integration of g, which is a transcendental process, and a certain tameness of g. So the idea is that g is built on some time function, and we would like to understand if the integration process destroys or preserves the time properties of g. So this is a very general question. And the general strategy in this talk will be the following. We will use a preparation theorems for the function g on cells, and we then deal with asymptotics of the function g on those cells. So in order to use preparation theorems, we are going to build algebra of functions based on subanalytic functions in order to use Paruzinski and Lyon-Rollin preparation theorem. This is a general introduction for this talk, and now I will give some motivation for the function g we are going to integrate. We have at least two motivations to consider oscillating integrals of the following form, integrals of this form, of functions of this form. We have two motivations. The first one comes from singularity theory. So in case m is 1, m is just the dimension of the parameters, of the space of parameters. In case m is 1, we can consider this particular function, and usually we take phi, the phase in the complex exponential, we take phi as an analytic function which has an isolated singularity at 0 g. And for the amplitude f, we take a smooth function with compact support. Then in this case, we know that using a resolution of singularity, we know that the integral of our function has an asymptotic at infinity when the parameter x goes to infinity in this form. So we have this asymptotics. And in case the coefficient APK is not 0, so in case this guy is not 0, then this guy is an eigenvalue of the monodromy of phi of multiplicity at least k plus 1. So there is an interplay between asymptotics and monodromy of the phase of the function. Okay, so this is the first motivation. Another one is a completely obvious motivation. In our framework where we try to study integrals of such functions. We also have the Fourier transform in mind, and clearly the Fourier transform is a very interesting object to study. Okay, so let's now go back to tenness, and let us consider subanalytic functions to start with. And I will briefly remind you what is a subanalytic function. We start with the definition of subanalytic sets. Subanalytic sets are a collection of subsets of Rn. So for any integer n, you choose a set of subsets of Rn containing all algebraic sets and stable under usual geometrical operation, such that a finite union and complement, stable under projection with respect to Cartesian product, and containing all graphs of restricted analytic functions. So you take a function f, which is analytic on this compact unique box. It means that f is analytic on an open subset of Rn containing this compact unique box. And you take the graph of this function, and as a set of Rn plus 1, you consider this set as a set of your class. Then you play with all possible operation, allowed operation in this definition, finite intersection, finite union, projection, and again intersection, union, projection, blah, blah, blah. And you define in this way, by saturation, you define the class of subanalytic sets. What is a subanalytic function? A subanalytic function is a function with a subanalytic graph as a subset of some Euclidean space. Okay. So it turns out that in case f is a subanalytic function in one variable, then asymptotically at infinity, this function is equivalent to a monomial with a rational exponent. Okay. Instances of subanalytic functions are the following. The log of 1 plus 1 over x for x in 1 plus infinity is a subanalytic function with graph in R2. Since this is the composition of the logarithm with a rational function, which is 1 plus 1 over x, that has a compact range. Okay, so composition of log, which is analytic with a rational function with a compact range, is subanalytic by our definition. But the sine function or the log function on the entire line are not subanalytic functions, because, for instance, log is not equivalent to a monomial with rational exponent. Okay, so this is what we can say for subanalytic functions. Now we denote by S of x the set of all subanalytic functions on a subanalytic set x in Rn. This is a basic class of function we are going to consider. And we have a preparation theorem for subanalytic functions that I will give in a very, very loose formulation. First of all, you can split the space of variables in a finite number of analytic cells in such a way that in restriction to such cells, the function may be written in the following form. So here you have a first coefficient in this product, which is a monomial coefficient in the form of y minus a function of x with exponent a rational number. Then you have h of x. So this is a subanalytic function, which is a function of a variable x only. So there is no y in this function. And then you have a function u. Oops, you have a function u of variable x and y. But we know more on u, more than the fact that u is subanalytic. U is in fact a unit. A unit means that U has a compact range, say in the interval 1, 2, for instance. So U is far from 0. And moreover, U appears as a composition of some convergent power series with some specific powers of Y. I don't want to go into details, but there is a very precise form of this preparation theorem, and this is this very precise, very sharp form we use in the following. I will skip over all technical details attached to the preparation theorem, because I'm going to concentrate my talk on uniform distribution phenomenon. Okay, I will explain a little bit later what are uniform distribution phenomena. So let's go back to our integration problem for now on, and let's see what is already known concerning integration of subanalytic function. So here we do not allow complex exponential function with a subanalytic phase, for instance. So we take phi 0 in the previous form, and we only consider f a subanalytic function with two variables. X is the parameter space, and Rn is the integration space. And the idea is to understand integration of f with respect to the second variable, the variable that lives in Rn. Two notation. The first one is the integration locus of f. The integration locus of f is a set of parameters x in capital X, such that as a function of y, f is integrable on Rn. Okay. And the second notation is the notation C of x for the set of constructible functions on x. Those functions are functions in the real algebra spanned by subanalytic functions and logarithm of subanalytic function. So those functions are can be written in the following form: polynomial in subanalytic functions and their logarithms. Okay. So this is the second algebra we built after the subanalytic algebra function, the constructible algebra. Of course, since we have log in this algebra, we have built here a larger algebra than the algebra of subanalytic function. Okay. And now the basic question is the following: if we integrate a subanalytic function, what kind of function of variable x we obtain at the end of the integration process? This question has been solved in 2 papers, the first one in 98 and the second one in 2000. Take f a subanalytic function, then the integration locus of f is still subanalytic. So we stay in the same category for the integration locus. I mentioned that in the case that f is semi-algebraic, the integration locus is also semi-algebraic. So for subanalytic functions or semi-algebraic functions, the integration locus stay in the same category. And for the integral of such functions, you leave the category of subanalytic functions and you have to enter in the category of constructible functions. In some sense, logarithm of subanalytic functions are you cannot avoid logarithm of a subanalytic function when you integrate subanalytic function, as you could guess, of course. So the next question is, can we continue on this integration process and stabilize this sequence of integration? In other words, is there some algebra of function stable under integration, starting from the algebra of subanalytic function? So next step, we integrate functions in the algebra of constructible functions, and by a result of Ralph Kluckers and Dan Miller, we know in this case that the integration locus is a zero locus of constructible function, and that the integral of a constructible function is still constructible. So at the second step, starting from subanalytic functions, at the second step, when you try to integrate the integrals of subanalytic functions, the process stops and you fall in a stable algebra of function, namely the algebra of constructible function. Okay. So now we try to do better than this, and we try to add oscillatory functions in the game. Okay, so now we consider the case where we have some complex exponential of some subanalytic phase, phi, which is not zero. And we build a firm algebra of function. The algebra of function spanned by the previous one, the algebra of constructible function, and complex exponential of subanalytic function. And the question is, if we integrate with respect to the integration variable y of f a function in D, do we find again a function of this algebra D of oscillatory functions? And the answer is no. No, D is not stable under integration. Why? Why? As you can see, this rational function here is a semi-algebraic function. So, of course, it is a subanalytic and is a constructible function, and of course, is a function in the algebra D. And if D was stable under integration, is Fourier transform, the Fourier transform of f would be in D. But the Fourier transform of f is in fact this flat function. And using preparation theorems, we can prove that functions in D have a convergent asymptotic expansion in this form. with Rn, Sn rational numbers, okay, decreasing rational numbers. And this guy, this coefficient, is a linear combination of complex exponential of ramified polynomial. Now, if you divide both sides of this equality by this leading term, this leading monomial and log term, since here you have a flat function, this coefficient, this coefficient has then to go to 0. But since this coefficient is a finite sum of complex exponential of ramified polynomial, I pretend that this coefficient cannot cancel. In fact, this coefficient oscillates. This is a fact that I will prove now. And to prove this fact, I have to explain what I mentioned earlier in this talk. I have to explain the notion of uniformly distributed mode 1 functions. So this definition is due to Hermann Weyl. Take a finite family of functions Pj from R to the j. And now consider the fractional part of P of t. Fractional part of P of t is in the interval 1, 0. Here. Now, take here an interval or a box in this unit box, compute the volume of the variable t up to capital T such that the fractional part of P of t is in your box, divide by capital T in order to normalize, and take the limit as t goes to infinity. And in case you get the volume of your box I, you say that this family is CUD mod 1. So the picture is the following. You take I here, you take all the translate of I by unit vectors, okay? And then you look at the set of variables t such that those variables are sended by p in your translates. Okay. Now you compute the length or the volume of all those variables, and you normalize by t. And if the limit as t goes to infinity of this normalized volume is the volume of your box, then your function is CUD mod 1. Okay. So now proposition, take a family of polynomial functions independent over the integers with no constant term. Then when you ramified those polynomials, you get a CUD mod 1 family. And now, using this property of being CUD mod 1, if you take distinct polynomials with no constant terms, and if you take a finite sum of complex exponential of those polynomials ramified as in the previous slide, then you can prove that the set of variables where your sum of exponential is bigger than some epsilon is big. is big in such a way that integrating 1 over y on this set gives you infinity. So as you see, as a first consequence, first obvious and easy consequence, this kind of sum cannot go to 0 when y goes to infinity, since this set has not a finite volume, for instance. So the red fact is proved using uniform distribution mode 1. But we have better than this. We can try to define uniform distribution in families. So now I take a family of functions of the variable y, and x is the parameter of this family. And we take the same kind of definition, but here you require that the limit as capital T goes to infinity is uniform in the parameter x. So uniformly in the parameter x, this guy goes to the volume of I. And now here is the two propositions we can prove with this assumption of uniform distribution. Take a family of polynomial in y with analytic coefficient in x. So in particular, you have a family of function with parameter in x. Assume that this family is CUD mod 1. So it's not a big deal because you can consider, instead of this family, a basis in this family over the integers, and then you get CUD mod 1 families. Okay. Then we have the following picture. The picture is the following: there exists some epsilon, there exists some alpha, there exists some compact set K in the space of parameters, and there exists some sequence of subset Xn of K with positive volume uniformly bounded from above, such that for each n there exists yn and zn. Oops, sorry. There is yn and yp, such that your sum here is larger than epsilon at yn in case x, your parameter, is in xn. So representing the graph of the module of S, you see this phenomenon. You see this set xn, you see this set xp. They are moving when you go from n to p, and for parameters in xn, the module of S is larger than epsilon. And for parameters in xp, which is different from xn, the module of S is also larger than epsilon, and so on. So we have a kind of wave phenomenon going to infinity. Second proposition is quite the same proposition, but here we have up and down waves in this proposition. We have a sequence of subset xn of x, and we have two sequences going to infinity, yn and zn, such that the difference between S at yn and zn is larger than epsilon. So here we have up and down waves going to infinity in a moving set of parameters xn, but with uniform volume bounded, positive uniform volume bounded from above. Okay, so you have to keep in mind those pictures. instead of the statement with all those quantifiers. And now again, I come back to my integration problem. So remember that our algebra D is not stable under integration. The game is now to find the smallest algebra containing D and stable under integration. So for sure, this algebra exists, but we'd like to describe, in fact, this algebra in terms of generators. So we'd like to describe in the simplest way as possible this algebra in terms of generators. So the idea is to add to D, which is D is described by generators. Remember that you have subanalytic functions, logarithm of subanalytic function, and complex exponentials of subanalytic function. Now we want to add transcendental terms to D in such a way to generate a stable by integration algebra. So we consider for this those terms. The gamma terms defined by this integral formula. So here you see you integrate h, which is a subanalytic function, with respect to the real variable t. You multiplied h by an integer power of log t, and you also multiply by the complex exponential e of t, okay, e of it. So this is, of course, a term which is not in D, given by this integral formula. And now we consider the last algebra we have to consider in this talk, the algebra E, spanned by D and the transcendental terms gamma. And here is the stability theorem. If you take a function f in E, then there is a function h in E such that the integral locus of f is a set of zeros of h. So again, the integration locus of f appears as a zero set of function of a function in the algebra E, and there exists a capital F function in E such that the integral of f with respect to y is a function of x, which is capital F. So you stay in the same algebra E after integration. So we have an explicit presentation of this algebra. And in fact, E, as you see, is defined as a module, not as an algebra, because we have no guess here that the product of two gamma terms are a function of our algebra D. In fact, once you have the stability theorem, it's easy to see that E is an algebra, meaning that the product of two gamma terms is in our algebra. Because take the product of two gamma terms, then this is just a double integral of a function of this kind, and you see that a function of this kind is a function is the integral of a function of our algebra, and by stability theorem, the product of gamma HL and gamma H prime L prime is still in E. So E turns out to be an algebra. Okay. So the first corollary is that we have a complete description of the smallest algebra or collection of complex algebras containing the subanalytic functions and a complex exponential of subanalytic functions. And in particular, E is an algebra which is stable under Fourier transform and which contains the subanalytic functions. Okay. So now I'm going to explain how to prove the stability theorem for E. An element of E is a sum of generators of the following type by definition. F is a constructible function. Remember that a constructible function is a logarithm in subanalytic functions and logarithm of subanalytic functions. A complex exponential of a subanalytic function and a transcendental term gamma. Now we introduce a definition, the following notion of super integrable generators of the algebra. What is a super integrable term? You plug absolute value everywhere you can in the integral defining the gamma term and around F. Then in case, after plugging absolute value everywhere you can in your term here, you get an integrable function, then you say that T is an integral, is a super integrable generator. Why do we consider super integrable generators? Because it's not difficult to see that in case T is a super integrable generator, then the integral of T is in E. So we have almost for free stability under integration of super integrable generators. Why? Try to integrate T. So remember that in T, you already have an integral defining the transcendental term gamma. So in fact, you can use Fubini theorem because you have super integrability. Since you have super integrability, you can put all your integrals at the left side, and you get such integral here. Now, you can assume that your generator T has no transcendental term, since you are going to integrate over Rn plus 1 a function which is in fact in D. That means with no transcendental term. But in this case, you just perform the following change of variables z equal phi of x and y. Okay. So now you just have the complex exponential of the function z, and then you use preparation theorem for h in order to let appear monomials with rational coefficients, and then you see that you obtain an integral of the gamma form. And gamma, of course, is in E. So using Fubini theorem and using preparation theorem, almost for free, up to technical details, horrible technical details, you have stability integration for super integrable terms. So now the question is, what to do with not super integrable terms. And in fact, we have a splitting lemma. We have a splitting lemma. If we start for a general function f in E, then you can find two sets of indices, J super and J bad, and generators S of j, B of j, such that F is a finite sum of the Sj's plus a finite sum of the Bj's with Sj's superintegrable. So for the first term here in this sum, we know that regarding stability under integration, we have no issue since we have superintegrable terms. And the Bj's are not superintegrable terms, okay, but there is no transcendental terms in the Bj's. So what you lose here is superintegrability, but what you obtain is that there is no gamma in Bj. Okay, this is the splitting lemma. And here, the exponent on y is larger than -1. So in other words, this part, this coefficient in y is not integrable at all. This is why Bj is bad. Bj is bad since a priori this guy is not at all integrable with respect to y. Okay, but in some sense, Bj is good because there is no gamma in Bj. How to prove the splitting lemma? We expand the h function in the definition of the generators of the algebra E. We expand as a power series, and then we integrate by parts several times. So if we integrate by parts, we let appear terms with no transcendental, since we have integrated by parts, with no transcendental, and those parts, if they have a very negative exponents, they are superintegrable, and if not, they are in this. They are the Bj. Okay. So this is only preparation theorem and integration by parts. This is a splitting lemma. So now, with the splitting lemma, we can easily prove the stability theorem. I claim that the only possibility to integrate the sum of the Bj in this equation, the only way to integrate the Bj, the sum of the Bj's, is that the coefficients here is 0. In other words, this coefficient here, considering the exponent here, is not integrable, but summing all those bad terms Bj, there is no compensation coming from the complex exponential or ramified polynomial. So the only possibility when you take the sum of the Bj to get an integrable function is that all the Fj's cancel. There is no compensation in complex exponential sums. So in this situation, the integral of f on the integration locus is only the integral of the superintegrable terms, but we know that superintegrable terms give integrals in our algebra. So we are done. Up to the red claim here, we are done. How to prove the red fact? Again, we use uniform distribution mode 1. So we consider Bj, written in this form. Pj are distinct polynomials. And now you take a sum of such bad terms, bj's, okay? And by our assumption, we know that the exponent upon y are larger than -1. So we have this sequence of inequalities. The integral of the sum of the bj's is larger than 1 over y, the sum of the exponential, of the complex exponential polynomials. But remember that we have uniform distribution for such a sum. So this guy, this integral here, this integral is not finite. So this sum cannot be integrable. And this is the end of the proof of the red fact. So now we are done with the stability theorem, and we go further. And we look at completeness with respect to our algebra, and we go to L2 Fourier transform, the Plancherel transform. So we have a LP completeness theorem. The statement is the following: take a sequence, a family, in fact, a family of function, a Cauchy family in LP. Then this family has a limit in the LP norm, as a limit which is a function in E. So what we know by completeness of LP is that the Cauchy sequence of function in LP has a limit in LP. But if we start with functions from E, the limit is in fact in E. Okay, so there is a stability under limit with respect to the LP norm for our algebra. And as an immediate corollary, if you take the intersection of our algebra with L2, then the Fourier transform defines an isomorphism from this intersection to itself. Okay, so we have an automorphism of algebra with respect to the L2 norm. How to prove LP completeness? Since LP is complete and since our sequence is Cauchy, then there is a limit in LP. This is for free. But there is also a sequence of parameters such that almost everywhere this sequence goes pointwise to a function, to the function f, which is in LP. Okay, so we can go from a limit in LP to a pointwise limit almost everywhere, up to taking a sequence of parameters. Now it is enough to prove that the family Fy goes almost everywhere to a function g of our algebra, since almost everywhere f and g has to be the same. So on some cell, we can write our family in the following form as a finite sum of generators. And of course, since we look at a pointwise limit, we can assume that Rj are larger than -1, since if it knows the case, you can see that Fy goes to the zero function. So at least we can assume this. We can assume that the parameter here is at least -1. Pj are polynomials, and Fj, the coefficient Fj, are in E. Okay. So in fact, the interesting case is the case where the maximum of the exponents Rj are larger than 0. Since if not, this function goes to 0 and we are done. So we assume that here the multiplicity term here appears with multiplicity Rs, which is at least 0. Then we can factor out this this term, and we have here a dominant term, capital S, which has the form again of a sum of a complex exponential of ramified polynomial with coefficients fj of the variable s. But now remember that our ramified polynomials are uniform in X, uniformly distributed mod 1. And remember that we have this wave phenomenon. So since we have this wave phenomenon, you see that there is no possible convergence of this guy, S. And remember that we have almost everywhere convergence of our sequence. So in fact, since this guy goes to infinity in case R and S are not 0, we know that if the sequence converges almost everywhere, then R and S has to be 0. So let's assume in this writing that R and S are 0, then F has this form. There is no coefficients here in Y and log Y. Again, S is the same sum of a complex exponentials. Again, the polynomials is a family of uniform distributed polynomials and uniformly in X. So we have our second proposition, remember, the up and down waves at infinity. But in this situation, there is no chance that our starting sequence Fy is a Cauchy sequence. Since we have between Yn and Zn a difference which is at least 2 epsilon, remember. So since this sequence cannot be Cauchy, this is a contradiction. So we cannot have Rs 0. And we are done. So we are now in the situation where our function, in fact, goes to 0. And this is the end of the talk.
Thank you very much.